Hey, you can see my little work in progress here. I got been testing out basically the power circuitry. I was planning on converting the whole circuit, minus the raspberry, of course, the whole thing to a breadboard, but that's annoying to solder. So I figure I'll just do the power. I think you don't want your power stuff running to the breadboard. So, and I got it partly done here. Let me see if I can show you guys my breadboard. This is my buck converter all hooked up here. So I got my buck converter, and my idea was I wanted to power my the raspberry off of the buck converter, so I don't have to have a separate 5 volt power supply going to the raspberry. So I use this regulator here. The one on the left is the linear regulator. The one on the right is a power MOSFET. Yeah, and there's a freewheeling diode there, so that is what is going to connect to the solenoid, and these two bad boys are going on here, and probably a little bit like a on-off switch, mains power switch sort of deal, and maybe like a power indicator, maybe an indicator for solenoid activity. So yeah, this is going to be this guy. Let me show you guys here. My beautiful soldering job with my new soldering iron. Oh, isn't that lovely? What a beaut. But yeah, so this is probably gonna be pretty much full up once I get this stuff on here and a little bit more. And it'll be good. And then what I'm gonna do, I'm gonna transfer all this stuff plus some more stuff to whatchamacallit, to different breadboard, but I'm not gonna use these like jumper wires with the pre-made plugs. I'm going to use like very short trimmed to length wires, so it'll be a lot cleaner than this. And this, I haven't talked about it. Maybe I'll talk about it in a video before I show this video, but this is my flood sensor. So you can see here when the contact is made, this goes off, which means that there's a flood. Trust me, that's going to be useful. And this like I can separate these, but just have like a wet paper towel between them and it'll still go off. So I'll talk about that probably in like a different video. But yeah, here is the whole schematic of what I've got planned here. So on the top end here, you've got like the power stuff. This is all going to be on the breadboard. Here is the flood detector with whatchamacallit, op amp. And here is going to be a latch so that if this trips, this will set up. Anyways, yeah, that's about that. Thing is, your boy Chili here. Welcome back to Project Moisture. Today we're going to be looking at the hardware failsafes that I built into this bad boy. So, look at this diagram. It's like a kind of like a top level simplified block diagram of how it all works. We have a latch here. This is a very simple memory element with a reset and a set input. So you can basically pulse either of these to turn it on or turn it off, and it remembers that state. Here we have an AND gate, and what this is doing is it's acting like a kind of pass-through gateway to this valve hardware output. So this is going to control the actual valve, or technically controls the power transistor that controls the valve. And here is the input coming in from our computer, our microcontroller. And this here is the setting, the pin that allows us to say whether or not we are going to allow this signal to propagate to here. So if this one is low, then no matter what this one is, it could be high, 1, or 0, this will always be 0. Because it's an AND gate, right? They both have to be 1 for the output to be 1. So as long as this one is low, we prevent the valve from ever opening, right? Which is what we want. So this latch, when you start up the machine, the latch will be set. So it'll have a 1 in the output here. And that means that when this is 0, this is 0. But when this is 1, this is 1, which is what you want. But then what happens is if we ever get this signal or this signal to go high, either of those will hit this reset, will turn this to 0, and that will automatically prevent this signal from propagating to here. It will be blocked by this AND gate, basically. It's basically how it works. So any instantaneous pulse, basically, of either of these signals will trip the latch. And once this latch is tripped, once this goes to 0, that's it. It's game over, because there is no, as you can see here, I have nothing connected to the set input. Well, it's more complicated. I mean, really, it'll be tied to ground. It'll be grounded. But basically, there's no way to set this once it's been reset. So the only way to do it is basically to power cycle the machine. So as soon as something bad happens, we get a flood or we get a timeout on our watchdog timer, it's going to enter this kind of like fail mode state in hardware, and that's it. You're going to have to reset the thing in order to use it again, which is good, because if you have a software error, you don't want the software to be able to mess up your fail state. I want a hard hardware lockout, and that's what this thing is giving us here. So now the only real thing to look at is, well, how does the flood sensor work, and how does the watchdog timer work? So this circuit here, all of this is basically the flood sensor circuitry. And basically the way a flood sensor is going to work is you're going to have, 2 electrodes, 2 wires. If they're in water, there will be some conductivity between these 2 wires. They're not actually touching, but if there's an air gap, there will be, 0 conductivity. But in water, there will be some conductivity. I mean, water itself, it's a covalently bonded substance. So there's not a lot of conductivity in pure water, but I think there is a little bit, because you do have like dissociation with the hydroxy groups and your H3O pluses. But this isn't chemistry class, so let's forget that bullshit. Essentially, pure water, not a very good conductor, but tap water, which is what will be here, has some ions in it. It does conduct at a certain rate. It'll make a very, basically, when these 2 things are wet, it's going to look like there's a pretty big resistor between these 2 terminals. And so we want to detect that, basically that current flow, and amplify that to a logic signal level. And that's what this circuitry is here. This bad boy right here is a 471 op amp, a workhorse from probably like the 70s, 60s, or the 70s. And op amps are very nice because they're very simple. I could build an amplifier to do this job out of basic transistors, but I don't want to. And op amp does a very nice job. It has 2 properties that we like for amplifying small signals. It has a very large gain, and it has a pretty high input impedance. So if you apply a voltage here, not very much current is going to flow, and therefore it's not going to affect your measurements that much. If that makes any sense. Again, this isn't an intro to circuit analysis and circuit design here, so I can't go into all these details. But that's the general idea. The op amp, what it's going to do is you apply signals to these 2 inputs. Let's call them A and B. And what it's going to do is it's going to say, well, the output is equal to A minus B times your gain, where your gain, in this case, it's probably going to be equal. I don't know. I don't even know what it is, but it's probably somewhere in between 100,000 and like maybe 10 million. It's a very big. So if you have if the difference in voltages between these 2 terminals was 0.001 volts, then maybe it'll try to give you 1,000 volts. Okay, so you're not going to get 1,000 volts out, and I'll talk about that in a second. But takes a very small difference in these signals and it amplifies it into a much larger output at this terminal here. So how does it work? Well, so in the negative terminal here, it's called the inverting terminal. We're just going to put a constant voltage. So you can see here it's got 5 volts here. We've got a voltage divider. So you're going to have 2.5 volts here because these two resistors are the same, right? So you're going to have 2.5 volts, which is half of the rail voltage that we're using here. And then we have the voltage here. We'll call this A because I already labeled it A. So A minus 2.5 times our gain factor. Now you can see here we've got these two terminals here. These are our electrodes that will be, submerged together in water when we have a flood state. And this one is just ground. So this one's just connected directly to ground. And this one is connected to 5 volts via this pretty large pull-up resistor, 100K. So we've got a very weak pull-up to 5 volts, which means when there's no water here, we consider that to be an infinity resistance here. And so you're going to see 5 minus, so you're going to see 2.5 times, 100,000 volts. That's 250,000 volts out of here. Only, of course, it's not going to be 250,000 volts because that would be insane. Where is this voltage coming from? I don't know. So that's the ideal output from an ideal op-amp. Real op-amps have positive and negative supply rails, and so they can at maximum only output their positive. So at maximum this 5 volts in here would output 5 volts out of here. Simultaneously, if you were to short these two together, this would be ground, so you would have 0 minus 2.5 and you would get negative 250,000 volts, but of course we don't have negative 250,000 volts. The negative rail is connected to ground, so you would go from 5 to 0 volts output. Except that, of course, we can't have nice things. We don't actually get that much. You can't actually go up directly to the rail, especially not on a crappy op-amp like this one. So I believe when this thing is trying to push out 250,000 volts, what it actually gets is like maybe 3.5 volts. So the output can swing maximum up to about, I think, 3.5 volts. And it can swing down to a minimum of like maybe 2 volts or something. I measured it at some point. I don't remember what those values are. Our output swing here is like between 3.5 and maybe 2, or maybe it's 1.5. Let's just say 1.5. Whatever. Low is going to be 1.5. And that is when we have a short. 3.5 is when it's open, when everything's okay. Now that's a problem because that means we can't just drive our logic circuits directly from this, because our logic circuits want 0 for low and 3.3 for high. So we're pretty close to the high, but the low is nowhere near where we want to be. So what's a boy to do? Well, we're just going to convert and do a little level conversion there. So we'll have a transistor, and when it's turned on, it is going to connect this directly to ground. So when this is high, the output will be low. Easy enough. And when this is low, then we'll have this weak pull up to 3.3 volts. So you get 3.3 volts when this is low and this is turned off. And when it's turned on, this gets sucked down directly to ground. Very strong suck down, but a very weak suck up. But that's all we need, because we're only driving these inputs here, and they're very high impedance. There's that word again, impedance. So that's the thing, except the problem is, if you'll recall, this thing, the low out of here is 1.5 volts. If we were to put 1.5 volts here, that would still turn this bad boy on. That's a difference of 1.5 volts across here. that is greater than the threshold for this transistor, it will turn on. So that means we will, the output options from here are, let me see, this is turned on, so the output options are low and lower, which is not good. We want to be able to have low and high coming out of here. That's ideal. So our output levels from our op amp are not even compatible with just a basic transistor that we want to use for level conversion. What do? Well, we can just drop the voltage. So basically, we've encountered diodes before in the previous video. They act as like a one-way street for current, but even in the forward direction, they have a kind of like a constant current drop to them. It's complicated. It involves exponential functions, but at its heart, there is a constant voltage drop here. So let's say the voltage drop is 1 volt. I don't know what it is actually for this part, and I'm too lazy to look it up, but let's say it's 1 volt. So by putting this in here, now our output at this node is 2.5 to 0.5, which means this one is not going to turn on the transistor, but this one will turn on the transistor, which is exactly what we want. And hallelujah, we now have our level transformation. And here we have our 3.3 volt. What kind of logic is that? Like CMOS compatible logic, I guess. And Bob's your uncle. We use a weak transistor to pull this down. And when we get 3.5 here, we get 2.5 here. And this turns on, and this gets sucked down to 0. And there you go. Bob's your uncle. And when we have a flood here, you know, it's going to act like a resistor. And I don't know, maybe, I don't know how much it is going to be. Maybe it's like 20K. But it's going to be enough to put this voltage here to, you know, if this is 5, and this is, we got a voltage divider between these two here. I'm not going to do the math, but like, let's say it's like 0.8 volts or something. I don't know. It's going to suck it low enough that this is going to be a very big negative number, and this is going to go down very low. By the way, when you're using an op amp like this, normally because the gain is so high, what you do is you do positive or negative, I should say negative feedback, and that is how you achieve like your specific amplification that you want. Like if you want to do 10x or you want to do 20x, you put some resistors in there, you do some negative feedback, and you're good to go. But if you use it in an open configuration like this, it's known as a comparator, which is important because we're going to see this again in the next little section of this video. But anyways, like I was saying, so that's the circuitry. But what about these electrodes here, right? I mean, they could just be 2 loose wires, but I don't like the idea of loose wires. The spacing between the wires is kind of important. They should be pretty close to each other because otherwise, like the resistance of water is pretty big, and it's obviously a function of how far away the wires are in the water. So we want them to be close, but we also don't want them to actually touch each other and give us a false positive on a flood. And we want them to actually cover like a large area of the tank, because if we get flooding on one side but the other side is dry, and that the dry side is where our wires are, we have a problem. So what I came up with is I decided, okay, so what I'm going to do is I am going to make a little sandwich just of some aluminum foil sandwich. So I'm going to have 2 sheets of aluminum foil, and I'm going to separate them with a sheet of paper towel. This is paper towel for you. So 2 sheets separated by paper towel, sandwich them together, and then you connect your wire to here, and you connect your wire to here, and Bob's your uncle. And paper towel, maybe like if we're looking at a top down, here's the top electrode of the aluminum foil. paper would be a little bigger like that. And then if any part of the paper towel gets wet, it's going to wick the water up into here. And once the water gets in between these two, we're going to get some nice conductivity. And I made it even better. What I did was I even opened up a little window, cut out the center of this foil like this. So this is paper towel, and this is paper towel out here. So now if we get like a drop of water in the middle, normally if it was in the middle without this window here, it would just sit on one of the things of foil, and it wouldn't get to the inside. There wouldn't be any conduction. But now if you got like a spill that's, somewhere in the middle of the foil, it can drip over to this part and wick, or it can drip over to this part and wick. So there's lots of options for wicking. And then I also sandwiched it with another layer of paper towel on this side and another layer of paper towel on this side. So we got like a 5-layer sandwich here. And that is my sophisticated sensing apparatus for floods. All right, so check this out. Here you can see one side of the thing. I got the foil attached to the center layer of paper towel here, and I got the cutout in the middle. And then on the other side, same thing. They're perfectly opposed there. So if any water gets in between those two electrodes, we're gonna have some conductivity happening. And here's what it looks like when you have the outside layers of paper towel. So I got our 5-layer sandwich there, and you can see light shining through there. Very nice. So that's how I did that. Now the last piece of puzzle for me was how do I attach now wires to these electrodes on the aluminum foil? Because it is possible technically to solder onto aluminum foil, but it's not easy, and it's definitely not what I want to be doing with my life. Originally I figured maybe I'll just kind of wrap the aluminum foil around, I'll fashion the wire into a little bit of a hook or something, and then I'll wrap a bunch of aluminum foil around there and twist it, and hopefully that'll be good enough. But I was I don't like that. I don't like that. So what I ended up doing was took a good old paper clip, and I wrapped wire around there, few twists, and then I soldered it up. And it's probably not going to be a really great solder joint on the paper clip, but wrapping with the soldering around there gives at least a good physical connection, and the conductivity is still fine. And once I've got my paper clip with my aluminum foil, I just doubled up a section of it. So I fold it over itself a few times, make it nice and thick, and then the paper clip can slide on there with good physical connection, and it's pretty good. It's a paper clip on there. It could still slide out, but it's even an advantage to be able to remove the clip if I wanted to replace the sensor or whatever. Oh, and another cool little thing I added, because like I said, the conductivity of water, even tap water, isn't great. I put a few sprinkles of salt in between, in this void here between the layers here and here, and between the layers here and here. And the salt grains kind of get trapped because of the way that I affixed these layers all together. So they got a few grains of salt trapped in here. So when they get wet, those grains of salt are going to dissolve, sodium and chlorine ions, and it's going to make the conductivity go way up. So instead of it being a resistor that looks like 30,000 ohms, it's going to be a resistor that looks like, I don't know what the resistance of water is when you dissolve a little bit of salt in it. Maybe it's like a 2,000 or 5,000, but it's definitely going to conduct water a lot better with a little bit of salt in there as opposed to with none at all. And I tested it, and it did work. I tested this whole sensor setup once with a throwaway that I built, and it worked great. So definitely a very nice little spill sensor there for you. So that's the flood sensor all taken care of. Now the second part of this is the watchdog timer. And essentially what this does is there's a feedback from this signal here that is actually controlling the valve, feeds back into our timer, and this timer measures how long this signal has been high, because we know that we're never gonna take more than, I don't know how many, maybe 40 seconds We never want to have the valve open for more than 40 seconds because it takes less than 40 seconds to fill the tank from completely empty to completely full. So if we're spending more than 40 seconds, then we're probably flooding the house. So if the valve just stays open for too long because of a failure in software, this thing will shut it down. Hopefully even before we hit the flood sensor. So there's like the two layers of protection. First, the watchdog timer should kick into action and prevent a spill at all. But if there is a spill, the flood sensor should kick in and make sure that the spill is only a very small one instead of, 20 liters of water on your floor. So, how do we do this timing here? That's the question. And in my mind, I was like, well, timing. Maybe we need a timing circuit. And when you hear the word timing circuit, you probably think of your old friend Faithful 555 timer. And so I kind of like looked at some designs that would use a 555 timer, and I was like, what are we gonna do with that? At the end, I decided no, 555 timer is not what we need. So what I ended up going with is very simple RC circuit: resistor, capacitor. Capacitor is, it's a voltage or charge, I don't know, whatever you want to call it, storage element. And if you've got a resistor and a capacitor in series, it charges up. Like let's say you're running it at 3.3 volts. It will charge up looking something like this. And we have asymptotic approaching your rail voltage of 3.3 volts. And so if you have a larger resistor, it's going to look like this. If you have a smaller resistor, it's going to look like this, and so on and so forth. If you have a larger capacitor, kind of same thing. It takes longer to charge up. So if I give myself a nice, because this thing has to take, like half a minute or so, on the order of half a minute to charge up, which is quite a long time in electronics domain. So we use a pretty big capacitor. I put 1,000 microfarad capacitor here, and then we can use this resistor to control how fast it charges up. Now, we have to decide, okay, there's got to be, let's say we want, say this is 30 seconds. So we want to time it for 30 seconds. That means we have to have some way of detecting when the voltage here exceeds a certain threshold. And we do that with a comparator. It's our good old friend, the comparator. So we have some reference voltage, and we pipe that into our negative terminal using a voltage divider. And that's a fixed voltage that we can choose. And so let's say we want that reference voltage to, I don't know, let's say it's 3.0 volts. And then Bob's your uncle, when this one goes above 3.0, this will go high. Otherwise, it'll go low. And for this, I decided to use a dedicated comparator part, but I don't remember why. Little side note, the reason why we use this JRC comparator part here instead of using another op amp is because the voltage levels, 3.3 volts, it's directly usable with our other logic. So by using this comparator, we don't have to add the diode and the transistor for the logic level conversion, which is very nice. And the reason why we don't use a comparator for our flood sensor is because we need the really good input impedance of that op amp. This comparator doesn't have that kind of input impedance, so we need to use the op amp for the flood sensor, but for our timer, comparator works fine enough, and it much fewer components. The op amps that I have, they're only able to run the crappiest rails that you can run it on are 5 volts and 0. So you couldn't do a 3.3 and 0. the dynamic range is just too squeezed out for that. So I think that's why I used a dedicated comparator chip for this thing. And also you can get 2 comparators on a single chip, whereas my op amps are just 1 op amp per chip. Whatever. Doesn't matter. The only thing that matters is that we got this RC circuit. We got the voltage divider here that determines your threshold voltage, which is your cutoff point here. And then we got this resistor here, which determines your charging. I can't word today. Your charging curve. Just words aren't working for me. But anyway, so that's this guy, which is not, by the way, in the circuit here. I added that later. But as you can see, like the output from here, basically, fucking layers on Photoshop, man. The output from here and the output from here, those both go into here and here. And that's how the sausage is made, my friends. That is how the sausage is made. And let's just check out the actual circuit here. We can see where all the corresponding parts are. I'm going to be honest, because I made some modifications. The circuit is basically what I've shown you in those schematics, but there were some minor changes here, some different logic refactorings. And those, actually, before I talk about this, now that I remember, go back here. So there is this latch here, but I didn't actually use a latch chip, even though I have one, because I had logic gates left over. Because in like a basic logic gate chip, you get like 4 logic gates in there. Let me show you. Yeah, so you'll have a chip like this, and I'll have a pinout, and it'll have like 4 logic gates in that bad boy. And I was using some of them to glue together, all the different parts of the safety circuitry, but some were left over. So instead of having a dedicated latch, dedicated WAM, what I opted to do was, let me see if I can get my layers back here. Yeah, so if you see this down here, stupid Photoshop layers. You see this down here, this is my latch. So you connect like 2 NAND gates or 2 NOR gates like this, where one of the inputs is from the other. You got this feedback, this dual feedback. That's how you make a latch, basically. And you can add more to that to make it kind of like a D flip-flop or a toggling flip-flop. But this is your very basic latch. You just need 2 logic gates, and so that's what I did. I hooked these 2 bad boys up, and that is your latch. And this is interesting. So the thing about this latch is they're both one. You could say one of these outputs or one of these gates is the high gate and the low gate. So one of them is going to be active, and that will suppress the other one. It's complicated. So the question is, when you turn the thing on, which one becomes the active one, and which one becomes the suppressed one? And it's actually an electronics race condition, which is I think that was maybe even a term that existed before multiprocessing race condition term existed. Anyways, you have this race condition, and it's not at the design level. It's not determined which one, what state it will be in when you flip the switch on. Now, in reality, because the silicon for these, the processes aren't 100% accurate, there are some discrepancy between devices. One of these devices will end up being quote unquote stronger than the other, and so it'll probably always turn on in that state. But it's also dependent maybe a little bit on what loads you connect and everything. At the end of the day, it's not good to just have your latch be random which state it turns on in. Like if this thing turned on in the what do you call it, the alarm state, the state where we've detected an error, it'll just stay in that state forever because there's no way of turning it the other way. By design, there is no software that can reset, or that can set the latch. It only can reset it. So that's where this comes in. And I think I removed maybe this resistor. So I believe this latch is actually active low. So when you pull it down, that will switch the state. If you pull the reset down, that'll reset it. If you pull the set down, that'll set it. And when they're both high, that's the state in which it just holds its previous state. It just remembers whatever it's at. And what we do here is we connect, we have a pull-up resistor high, meaning that normally this thing is pulled up high, it's not being pulsed, it's not being used, right? So I believe that this would be, if we were to correlate this with our previous diagram, this would be the set input. It's constantly being pulled up high, and so there's no way of setting the flip-flop. However, the trick is we also have this resistor, no, that's not resistor, capacitor that's pulling it down low. So when you flip the circuit on, the capacitor will basically appear like a short circuit. And so this thing will be low. It'll see a low. It will initially set the flip-flop. But then we've got this resistor here. Current flows into the capacitor. The capacitor, so if we look at here, it's going to, the voltage at this pin here, it starts off at 0 volts, but it's going to charge up to 3.3. So it starts off at 0, sets the flip-flop, but then it charges up and it stays high so that the flip-flop, this input now is not being used, basically. Pulling it high means deactivating this input. And now, if this input here, this input is also going to be high, and if it ever gets pulled down low, the flip-flop gets reset, and we have no more way of opening the valve. So that's just a little thing, a little piece of the circuit there that's interesting, how to enforce an initial state on your flip-flop. So anyways, back to our diagram here. Let's label all the different parts here. This is the op amp. This is the diode coming out of the op amp. I think, so these two wires here, these actually go to the electrodes. So that comes in here to the op amp inputs here. We've got a voltage divider. This is probably the voltage divider. And then this is the pull down. No, because that's pulled down. There should be a pull up. I don't know. Maybe this is the voltage divider. These two. Doesn't matter. We got voltage divider. We got a pull up resistor. We have our diode that is doing a little bit, dropping a little bit of voltage. We have our transistor that does our level conversion from our output to our logic levels here. And that's that. This is either a quad NAND gate or a quad NOR gate. I think it's NOR gate. I switched it up. Like the diagram you saw before, that was NAND gates, but I think I decided to use NOR gates because the logic just worked out better. I could do it with less components that way. And I think this one is just doing a logic inversion because I needed to invert one of the outputs or something. So we got another transistor here for a logic inversion, so I don't have to add another chip. And this is also, I think this is an AND gate. This is a 0-2 part. I believe that's AND. So I think this is the actual AND. I don't know. I think it might. No, because you see, we got these two tied together. Maybe this is a NAND gate. And if so, then this would be being used. I needed an additional inverter or something. I don't know. You know what? I don't know why I put all these chips in here. It's weird. But this, I might not know all the logic chips exactly, but I do know that this is the capacitor, the 1000 microfarad capacitor for our timer. This, I believe this one is the R for the RC timer. This controls the flow into the capacitor. And this potentiometer, this one controls the voltage divider for the threshold. This is the comparator, 2902 or 03D JRC. little comparator circuit there. I think it's a dual. There's actually 2 comparators in here. And yeah, that's about it. I think that's pretty much all the things here. These wires coming out, these go to the display and the touch input, and then they go into the Raspberry Pi. These are the I2C bus. This is the I2C bus itself. It's not very interesting. You just hook all the corresponding wires up together, and Bob is your uncle there. But yeah, that's all the hardware. That's all the circuitry. All done up.